In the second part of today's lecture, we'll discuss about characteristic of bending deformation of symmetric members. What do you mean by what do I mean by symmetric members? I mean, like when we have like a long aspect ratio beam, and if we consider the cross section of this beam, the cross section must be like a symmetric with respect to the plane that is orthogonal to neutral plane. And what is the neutral plane? The neutral plane is the plane where we don't expect any length change. Like suppose that when this beam with the symmetric cross section is under bending moment m, okay, then what you can expect is that maybe the upper part will be under compression and bottom part, lower part, will be under tension. Okay, and because we have to go through like from compression zone to tension zone smoothly, there must be a special section there where there is no compression and no tension. Okay, because there is no compression and no tension, we can expect that even though it can bend, the length would not change. We call that as neutral plane. Okay, if the neutral plane is if we have neutral plane, and if you assume a plane orthogonal to neutral plane at the center of this cross section, and if you found this mirror symmetry, you can say that this is a symmetric member. And in the later part of today's lecture, what you're gonna prove is that the neutral plane go through centroid point. Okay, so we haven't made any proof about this. We're gonna make a proof that neutral plane under the pure bending will go through centroid. Of course, if there is like if you have like a bending that is not pure bending, in addition to m, if there is like a n or v, then neutral plane would not go through the centroid. Okay, regarding the mathematical derivation and proof, you're gonna see that in next video. And let's also make a qualitative note on pure bending of prismatic symmetric member. What I mean by symmetric is the cross section is symmetric. What I mean by prismatic is the beam should have same cross section throughout the entire beam. Okay, if you have a beam with changing cross section area, if you have a beam with this kind of smooth changing area, you cannot call that as a prismatic beam. Okay, so now when we have a prismatic symmetric member under pure bending, we can summarize the characteristic of pure bending and some sign convention of pure bending in this way. So regarding the sign convention, we typically say positive m, the smiley thing as positive m, and the crying thing as negative m. So when you see these kind of pair clockwise on the left and counterclockwise on the right, you typically assign like positive sign for this m. When you have the opposite sign, then you have negative sign. Okay, and let's think about making imaginary cut here. When you make an imaginary cut, because this is upper part is compression and lower part is tension, you can also imagine that the m must act in this way to make a balance with the external force in the left side. So anyway, this one, these pair will give you positive sign. It's the same for the right side, because this is under compression, which means that there is a force from the right body to left body that acting on that direction to make a compression. It's opposite in the other direction, and as a action reaction pair, so regarding this left direction force, you're gonna have reaction to right side, and for this right side direction force, you're gonna have reaction in the opposite direction. So this direction force and that direction force corresponds to compression for right part and tension for a right part, so that you can have same kind of smiley moment on right part. Okay, so even though you can decompose the positive sign body at any point you're gonna see the positive sign convention preserves in left and right body. Okay, and the second observation and comments that I want to make is, for pure bending of prismatic symmetric member, each cross section remains perpendicular to long axis. Actually, this is not the case if you consider non-prismatic beam or non-symmetric members, but for symmetric members, we can say that each cross section remains perpendicular to long axis. And please remember that this only holds for pure bending. Then third characteristic you have to remember is cross sections. The y plane, x is the long axis. Y plane remains planar, and they rotate around the z-axis and deform within a plane, but do not warp. Okay, warping means like when you have this kind of plane. If you see something like this, you call that as warping. What number 3 says is that when you have some imaginary plane which is a complete plane in the beginning, even after the pure bending, the plane remains as plane. Okay, of course it is not the case for asymmetric weird cross-sectional bending or non-pure bending. And please remember this, that the third condition only holds under the pure bending of prismatic symmetric beam. And fourth characteristic that I want to tell you is the relative rotation between two cross sections is proportional to their distance along the axis, which may be similar to the description we had in torsional loading. Okay, so these are the assumptions we are making about the pure bending. Actually, we are making these assumptions for pure bending, and based on this assumption, we consider our mathematical derivation on stress and strain. But in advanced mechanics course, instead of making these assumptions, we're gonna prove that these statements are true under pure bending. However, because now we are in the undergraduate like elementary mechanics course, we're gonna make an assumption. First, these assumptions are from observations. Then we try to derive a mathematical equation based on this assumption. Of course, this is not full advanced discussion about mechanics. And if you want to understand mechanics even better detail, you have to take advanced mechanics course. Okay. So so what I mean by this fourth sentence is, when you take delta x1 like this long, or when you take delta x2 like this short, then you can think about the rotation angle delta theta 1 and delta theta 2, which pointing on like same point. Okay, of course this angle must be proportional to delta x1. Okay, so actually under the pure bending and prismatic symmetric member, whatever perpendicular cross section you are taking after bending, they're gonna meet at their extension of them would meet at one point. Okay, this is the observation of pure bending, which is stated in fifth sentence. The beam bends into a circular arc with a center at O prime and a radius of curvature low. Okay, so these are the assumptions that we can make about pure bending, and these assumptions are from observations, and I do not provide the mathematical proof. But starting from these observations, we will try to derive some equations for stress, strain, and the relationship between external loading, stress, and deformation, and curvature radius, low, and etc. Okay, as I told you, if you want to understand this in even better detail, I highly recommend you to take advanced mechanics course in forthcoming future of your life as an engineer. Okay, so by providing the assumptions that we're gonna make when deriving the stress distribution, let me close the video here. And regarding the mathematical description, I'm gonna get into the detail in next video.